Hello everyone. In the last video, we talked about latency and we saw how the low value of latency had a direct impact on the number of buffers. So that is, if you can reduce if you can reduce a single buffer on each clock path, and if you have millions of flops available on your chip, so you're actually reducing millions of a million x amount of area on a chip, and that's a huge save. Because in today's VLSI world, in today's world, if you see, you have lots of applications running on a smartphone, on lot of devices are closely packed on a single chip. So that is the clear advantage. You can, if you have more area available with you, you can utilize that area for adding some more applications or adding some more functionality on your chip. So that's a clear advantage of, or that's a clear win of having a having less amount of area. So that the one of the way to achieve the less amount of area is to keep a low latency between the clock path and the flop, because that is one of the components, that is one of the thing that is being spread out over the complete chip area. So yes, the clear advantage of having low latency is less number of buffers. Less number of buffers, you save an amount of area. Next advantage of having low latency is, so if you have low number of buffers, it will eventually lead to less number of routes. For example, all these things works on certain kind of algorithms. So one such algorithm is that when you start from the clock pin, it will search for the next input of a buffer. So the next input of a buffer is this one. Okay, next, when it moves from this point to this point, when the algorithm reaches this point, it will find it for the next input buffer, because since it has to connect from this particular output to the input of this buffers, it will search for the algorithm will search for the next input buffer. So it will search for these two, and the third, and when it reaches over here, the algorithm will run the third time, where it looks for the next input pin. So it gets the next input pin over here, and it connects over here. In this case, it finds the next input pin over here, and it connects over here. And that is the algorithm runs the fourth time, when it reaches over here, to find out the next input pin. So over here you see the same algorithm has been run four times, once at this point, once at this point, once at this point, and once at this point. Imagine if you have like tens of buffers placed over here, and you have tens of buffers placed over here. The search algorithm has to be run 10 times more over here, because you have 10 more buffers over here, you have 10 more buffers over here. So eventually the algorithm, if we have enough parallelization in the algorithm, it has to run 10 times more, because after every output of the buffer, it has to look for the next input. So you have to run that algorithm every time. So clear advantage that you see, it's the runtime reduction. If you have less number of, first of all, it will reduce the number of routes, and the second advantage is the runtime reduction, because building this tree will itself take an amount of time. If you plan your clock tree beforehand, you have saved an amount of runtime over here. It's clear reduction from 10x. It's a 10x reduction, if you see. And that too, we have like thousands of flops which is sitting in small area. So if you multiply the runtime with multiplied by the 1000, if you see that amount of time you save by building a clock tree. And the second impact that you see is the number of routes. If you have 10 buffers, there will be small routes which will be present in between these buffers. So you save those routes. If you save those routes, you save again. You again save some amount of metal. You again save some amount of area. So these all small savings leads to a bigger one, because this is not the only circuit that will be implemented on a silicon. This structure will be repeated multiple times on a silicon die, and will be printed. So so a small savings in this, let's say a small saving in this path itself will lead to multiple savings in the other chip, because this will be replicated on a silicon die and printed and fabricated. So a small saving in this area will be a saving in the other areas also, in the other dies also. So this is one more clear advantage of having low latency. And the third advantage that we have from low latency is the less power dissipation. So if you have we compared this with hurdle race. This was point A and this was point B, and we saw there were 3 hurdles over here. Now for example, there were huge number of buffers over here, like 10 buffers. So there will be have been 10 hurdles in this path, and you would have been doing 10 jumps over here. So clearly you're saving energy by having saving energy, and you're saving power by having low number of buffers, and which eventually turns up to having low amount of latency. So let's talk about this power dissipation in the next slide, which is the next quality check for us, which is the clock tree power. So let us look into the power thing in a bit detail, and we will have a separate set of classes that will be arranged only for clock tree power. So let us try to look into a few concepts of clock tree power over here itself. So we'll take the same circuit as an example. We have the launch flop, we have the capture flop, and we have a clock pin which is supplying the clock to the launch flop and the capture flop. So over here I have written the clock tree power is a function of, the first point is very clear from the previous one, from the previous quality check parameter, which is the latency. So as I said, that number of buffers will reduce the amount of latency, and that eventually will reduce the number of jumps, which will eventually reduce the number of the amount of clock tree power. The second thing is the clock tree power is a function of the transition as well. Transition is basically 0 to 1 transition and 1 to 0 transition. So the power is a function of this. How it is a function of both of this? Let us try to look into one example of this. So for example, you have this buffer. Internally the buffer is nothing, this particular buffer, it's nothing but a combination of 2 inverters. Okay, so it is like 2 back-to-back inverters that is connected over here, that basically forms a buffer over here. So now let's look into the characteristics of one of the inverters, and that particular characteristics can be expanded to a buffer or can be expanded to any circuit. So let us try to look into the basic characteristics of this small inverter. If we expand this inverter, so I should have expanded it only for this inverter, but let us try to look into the buffer as a whole, and the inverter as a single element over here. So we are looking at an inverter over here. Inverter has got a PMOS at the top and NMOS at the bottom. This is a very famous structure that we have seen for an inverter circuit. So the first kind of power, let us try to look into what happens in this scenario. So when you see at the input moves from logic 1 to logic 0. When it is at logic 0, your PMOS turns on, your NMOS turns off. So PMOS, if you see a small dot over here which says that it accepts inverted logic, so which means this is a direct connection, which means when there is a logic 1 over here, NMOS turns on. When there is a logic 0 over here, your PMOS turns on. So in this case you have, let's look into this particular scenario where your input is at logic 0. Basically it is switching from logic 1 to logic 0, and when it reaches over here, it is at stable condition. So you have a 0 over here, you have a 0 over here. When you have a 0 over here, your PMOS is on, your NMOS is off. Let us try to draw that thing. So basically you have a zero is nothing but a VDD, sorry, a VSS. So you have the PMOS, you have the gate of the PMOS which is grounded to VSS, and the NMOS we have removed it because at this scenario your NMOS is off. So what happens when when you have a zero voltage getting at the gate of the PMOS? You have this current, that you have this capacitor that needs to be charged, and the capacitor gets this charge from the supply voltage. So your PMOS acts as a closed switch, and this particular capacitor gets its charging current from the VDD. So when we say that a capacitor is charging, it means that it draws an amount of charge from the VDD, which means the VDD has to supply that particular charge to this particular capacitance. And when you say we are drawing some charge, we are drawing some amount of, it's as good as if you have a you have a tub, if you have a water tub and you have a tap which is present over here. If you turn on the tap, you will have some water that flows from high level to low level, and then you close the tap when this particular thing is completely filled. Similar thing, you have to open your tap whenever you reach to zero. You open your tap and you have to charge this particular capacitance, and then you close your tap. You don't close your tap unless and until this is completely charged, and once it completely charged, you close off your tap, and that's all. You get a logic 1 voltage over here. That's how you see a logic when you go to logic 0, you see a logic 1 at this particular point. So since I'm running out of time over here, I'll just leave you with this concept that whenever you have a switch over here, there is a tap that gets open, and some amount of water, some amount of charge flows from this area to the capacitance. And let me leave you with that note. In the next video we'll be seeing that how this particular phenomena, how this particular scenario affects the power, and this is how this gets related. This is how the latency term gets related to this particular thing. So we'll be trying to bridge that particular gap in the next video. Thank you.